All right, so let's take a look at the relationships between a rate law and the mechanism. So first off, we're going to take a look at the simpler case. And so this is when the RDS, the rate determining step, that's the slow step, when this comes first, it's the only thing that matters, right? If your first step takes 20 minutes and your second step takes 1 second, then your overall reaction is going to take about 20 minutes. So example, here's the overall overall reaction here we have. We have NO2 combining with carbon monoxide to form NO and CO2. And then we can take a look at the elementary steps here, or we can propose some elementary steps, right? So we'll say in elementary step 1, we have NO2 colliding with another NO2 molecule to form an NO3 and an NO. And we'll say that this is the slow step. So this is the rate determining step. And then in the second step, an NO3 that we previously formed reacts with a carbon monoxide to form our NO2 plus CO2. And so you can tell if you cancel things out that are on the same side, right? So if you cancel out these two NO3s, you will then get, and also, these two NOs, you'll get the overall reaction, right? And so if the first one was slow, the second step is fast here. And so we can write a rate law here. And because our first step is the slow step, it is the only thing that matters. And so we can write straight away, rate equals K NO2 squared, right? The only thing that how fast this reaction is going to go, it only depends on NO2, because as soon as that NO3 is formed, it's going to react with the CO very quickly, right? So when the RDS is first, it's the only thing that matters. So maybe this is the mechanism that you propose. You're like, oh, okay, I see this overall reaction. This is how I think it's happening. You could then, solve your rate law, and you're like, okay, if this is happening this way, it must have this rate law. And then you could experimentally find the rate law. And if it matches, then your mechanism is valid. It means that it could be an option. It doesn't prove that it is happening this way, but it proves that it could be happening this way. If your experimental rate law does not match your theoretical rate, then your mechanism is wrong, right? It does not happen that way. The experiment reveals the truth. And so here's just kind of the energy diagram for this two-step kind of mechanism. And so we'll see the first step is very high activation energy, and then the second step is very low activation energy. So the first step is going to be much slower than the second step. So it's step 1 that determines the overall rate. Remember, again, the top of these humps are these transition states. We cannot isolate them. And then this stuff in the middle are called intermediates. And this stuff we can isolate. So we can isolate intermediates, which are in between two transition states, but we cannot isolate transition states themselves.